So now let's proceed to the Laplace transform. So in previous discussions on EEE130, analyzing circuits with a wide variety of inputs and responses are modeled by differential equations, whose solution describe the total response behavior of the circuits. So the Laplace transform is a powerful method as it turns or transforms the differential equations into algebraic equations, thus greatly facilitating the solution process. So functions must be a unit step function, so meaning no value at t less than 0. So the definition of Laplace transform. So the Laplace transform is an integral transformation of f of t from time domain to the complex frequency domain f of s, where s is a complex variable. So take note that 0 minus indicates time just before t equals to 0, where the origin and any discontinuity of f of t at t equals 0 is included. So these are Laplace transform pairs. So this discussion is just a quick overview of the Laplace transform because it is discussed in ENS 181 or in in engineering mathematics, which we have already taken up. So just a quick overview of the properties of the Laplace transform. So we have these 10 properties. The first is the linearity. The Laplace transform of a linear combination of functions is the same as the linear combination of the transforms of the individual functions. So time scaling. So time expansion at when the absolute value of a is greater than 1 will cause a frequency compression. So looking at this equation right here. Ah, time compression, which is time compression where a is less than 1 will cause a frequency expansion. Because if this a right here is less than 1, this term will increase. A is greater than 1, this term will decrease. So time shifting. Delay in the time domain causes multiplication of e to the negative as with the Laplace transform of the function. So if you have time shifting in the time domain, the Laplace transform of it is just the Laplace transform of f of t times e to the negative as. Next is frequency shifting. So a frequency shift in frequency domain causes the function f of t to be multiplied with e to the negative at times u of t. If there is a frequency shift, this causes the function f of t to be multiplied with this. Next is for time differentiation. For a single derivative of f of t, the Laplace transform is, so if you get the Laplace transform of the first derivative of f of t, we have s times the Laplace transform of f of t minus the initial value of f of t, or in this case, the value of f of 0 minus. So if we have repeated derivatives, or the general equation is given by this equation. So time periodicity. So for a periodic function f of t with period capital T is only needed to obtain the Laplace transform of the first period f1 of t. So the time periodicity property states that the Laplace transform of a periodic function f of t is equal to the Laplace transform of the first period f1 of s over 1 minus e to the negative capital T times s, where T here is the period. Now, initial and final value theorems. So the initial value is at f of 0, and the final value is at f of infinity, or where t approaches infinity. So in Laplace transform, the initial value would be f of 0 is equal to the limit of s times the Laplace transform of f of t, where s approaches to infinity. And the final value would be f of infinity equivalent to the limit of s times the Laplace transform of t, where s approaches to 0. So now we'll have a first example. So get the Laplace transform of the following. Before we get the Laplace transform, first we need to get the equation g of t, or the expression g of t. So g of t, we have 10. So this has a time shift, t equals to 2, time shift of t minus 2, and then it becomes 0 at t equals to 3. We have u of t minus 3. We can easily get the Laplace transform. We have Laplace transform of u of t minus 2 is just, so we have a time shift. We have e to the negative 2s times the Laplace transform of f of t, which is just 1 over s, minus e to the negative 3s times 1 over 4. We have 10 over s times e to the negative 2s minus e to the negative 3s. So next, find the plus of the following function. First, similar with the previous example, need to get the expression h of t. H of t, so the function has a value of 10 from t equals to 0 to t equals to 2. Then u of t minus u of t minus 2 plus 5 u of t minus 2, and up to t minus 4. We have 10 u of t minus 5 u of t minus 2 minus 5 u of t minus 4. If you're wondering if this is the right equation or expression for h of t, so let's get the values at a certain time. So we all know a unit step function. If we have u of t, this value is 0 if t is less than 0, or this is 1 if t greater than 0. So let's say let's take the value of h of t at t equal to 1. H of 1 equal to 10 u of 1 minus 5 u of 1 minus 2. We have minus 5 u of 1 minus 4. So u of 1 from this expression, from the definition of our unit steps, we have this is equivalent to 1. And 1 minus 2 is just negative 1. So this is 0. And 1 minus 2 and 1 minus 4 is negative 3. So this is also 0. The value of h at 1, 10, which is true. Now let's proceed to getting the Laplace transform of h of t. We have h of s. Laplace transform of this expression or this term is 10 over s minus, we have a time shift 5 times e to the negative 2s over s minus 5 e to the negative 4s over s, or this is equivalent to 5 over s times 2 minus e to the negative 2s minus e to the negative 4s.